Okay, so now this videos in this series of robotics will be about adversarial attacks. Just like there are adversarial attacks for the machine learning pipeline or for the machine learning model, there are adversarial attacks for the robotic pipeline as well. This is what adversarial attack looks like for deep networks. There was a panda and your uh, like machine learning model, maybe you were detecting, let's say you were using any object detector, let's say YOLO, and it detected like it is a panda and the model was 57% confident. Now after addition of a so minimum amount of noise, which is equal to 0.007 of this thing, and when it is added to this picture, and again the same picture is detected by the same detector, now it showed this prediction. Now it is 99.3% confident that it is not panda but gibbon. Hope so I'm pronouncing this word right, and I don't know what gibbon is. But the whole point is that you have added something in your picture that you are not able to detect with your eyes, but there the noise was like good enough that it made your machine learning prediction wrong. Similarly, there are some patches that if added in the picture would make your uh, prediction of detector wrong. And there are many examples. So just like this, there are adversarial attacks for slams as well that will obviously like result in tracking loss, or maybe like loss of like map positions, etc. So this is what adversarial attacks on robotic pipelines mean. So these are the lecture slides I'm using to like teach you this. Okay, so usually like machine learning or the learned feature are easily manipulated, or easily what you can say, you can easily add adversarial noise to the learned feature, the feature learned by your machine learning model. But handcrafted features like surf, shift, or fast, these two can be deceived. And uh, obviously there are many papers on this, but in this slides or in this video we will be using a paper published by them, and the title was adversarial examples for handcrafted features. The whole point of this paper is to like make adversarial noises so that your orb slam can be deceived, your ptam can be deceived, for example, your bag of words can be deceived. So like this is what they have done. Again, this is another example. This was your original picture, and this is with this is like the same picture, but they have added a noise in it, which you cannot obviously distinguish with your eyes, but there is a noise inside it. And you can see here, okay, if you have tried to match this picture with obviously its own, then itself basically, then there are many matches. And when you have tried to match this one with this one in which there was a noise, then see, now you are not able to find so many matches between these two images. These lines indicate matches. Hope so you understand it. So this is very dangerous thing for slams. Obviously they can lose tracking, they may forget loop closure. So again, these are some examples. Okay, this was the actual path that should be taken by the slam, but after addition of noise, like it changed the track. Similarly here and here, it happens when there is an adversarial noise in the environment. Here is the table of the results after their adversarial attack. After attacking these slams, orb slam and bag of words and fab map, what they have got two data sets. One they have made their own, and secondly RGB DOM data set. It had 12 loop closures and 3 were detected by orb slam before addition of adversarial noise. But after adding the noise, 100% loop closure failure happened. So the adversarial attacks were so strong that these were able to deceive orb slam. Similarly, it deceived bag of words and fabmap. This is percentage. PMSD stands for percentage matching score declined. And see, it declined 36% in RGBD TUM dataset, and in their own dataset it declined to 26.8. Therefore, there are other parameters as well that were greatly reduced after addition of adversarial noise. Okay, now there are many types of noises, adversarial attacks basically, that they added in the environment so that the slam can be deceived. First noise is average scared mask perturbation. What they did is, for example, there was a picture, and there were, for example, different features detected previously, like before addition of this perturbation. What they did, they took 3 cross 3 kernel around the feature. Then they added noise in this region, and after that they did imprinting mask. They applied imprinting mask that, let's say, colored it, or basically their aim is to remove this feature from here. Okay, and then this was how they did previously. For example, if the feature was here, now it is like after addition of this imprinted patch it is removed. Now obviously there is no feature now, the feature is now not detecting, so obviously it will result in maybe tracking loss, or obviously slam is keeping the track of its position due to the features in the environment. So now features are attacked, so there can be many consequences. Secondly, in this attack they were using a kernel, and then they were blurring the region of the kernel, like beneath that kernel, the region beneath that kernel. But here they used a bit more greedy approach according to them. Here, if they detect a feature somewhere, what they did is they added perturbation along dominant direction of the surf. Obviously you know that surf feature has direction as well, so they added perturbation. For example, they added perturbation along the direction of the surf, and it's perpendicular to the direction of the surf, and it looked like this, something like this. It was cross, the noise was added in cross, and then same impending mask was applied, and this is how the final output looked like. So this is pretty much uh, the same type, but they are not using the kernel for it. So again, the goal was to remove the feature from here, and it is removed. Now in the third type is pixel to pixel perturbation. Here again they took a 3 cross 3 kernel. For example, this was the picture, and here was the feature that was detected previously before addition of noise. They took a kernel, and it was obviously, if it was 3 cross 3, then obviously there will be 9 pixels. Now they changed these 9 pixels, and how they changed it, now they are applying some strategy to change this pixel. They used value of this pixel, and like the upper pixel to this one, and the immediate left pixel to this one. They averaged the value of here and here, and replace this value with average of these two pixels, and you use this formula. And they did this with each pixel in this 3x3 kernel or 5x5 kernel, and they managed to receive the slam this way.